And the first talk is about Andrew Ludlow, who leads a group in NIST, making currently the best clocks that we have in the universe. So yeah, looking forward to your talk. Thank you.
There's some aliens on my right now saying,
who's offended? Yeah, I'm sure they've got orders of magnitude on us.
Did you see our paper in galactic letters?
All right, well, it's great to be here with you. Over the next little bit, I'd like to tell you a little bit about how we've been using kind of latest generations of clocks for measurements that explore new physics, including searches for dark matter. I'll begin by maybe taking a look at more conventional use of atomic clocks in the search for new physics. So this is an experiment that actually was carried out over the last decade and a half, where they were searching for violations in local position invariance and using the Earth nominally as the laboratory, and just in the normal orbit around the Sun, by experiencing the changes in the gravitational potential and looking at the differences between two particular types of atomic clocks here, hydrogen masers and cesiums. And this is not by accident that they've chosen these types of clocks. These clocks are operated normally as part of international atomic time, so it was a case where they actually just had a lot of good data that they could analyze, looking for changes in the ratio between these two clocks that might suggest some type of LPI violation, some non-zero beta term down here. And so, like I said, they actually accumulated data over about a 15-year interval. In particular, over the last half of that, they actually had quite a bit of measurements. So there was 4 masers involved and actually 8 cesiums. Because of satellite links between national metrology labs around the world, they were able to get a fairly large number of participants in this. And in the end, what they were able to see is they're consistent with 0 at the 2 × 10⁻⁷ level for this LPI violation. Okay, so that'll be kind of a framework for what I'd like to discuss as we think about how to use the newest, latest, and greatest types of atomic clock systems for making measurements, in part like these types. So I'll be talking almost entirely about optical clocks then. There's been several decades of work already behind all of the great progress that these optical clock systems have made. And right now, I would say that, at least for me, the success of these systems, and they're really maturing at this point, is built on the 3 pillars of optical coherence, quantum control, and precision measurement. And just by way of introduction, I'll say 1 or 2 brief words about each one of those things that goes into making these systems work as well as they do. So in terms of optical coherence, in the simplest story, because the clock transitions that are being interrogated are in the optical domain, they simply divide time into really fine intervals, and you get an enhancement factor of something like 10 to the 5 compared to conventional clocks. And almost everything else about optical clocks is a footnote to this one single detail. Really, nature does all the hard work, and for the most part, we just come along for the ride, benefiting from this really high operating frequency. Of course, we need coherence as well at that high operating frequency, and so that's one other important detail, and that one we do have to work quite a bit at. And you can see that anomaly in a typical expression for what the statistical precision of a clock would be. Scaling as the ratio of whatever the line width that you can resolve given by the carrier frequency. So we work really hard to get narrow line widths, and we benefit mostly by nature giving us a large frequency. So for that coherence, that already limits quite a bit the number of atomic species that are interesting for making these types of optical clock systems. One particular attractive atomic structure is that given by group 2 species that have these spin singlet and triplet states that usually have very, very weak couplings between them, violating multiple selection rules. This lowest lying state, triplet P0, often has a lifetime of many tens of seconds, for example. And that allows us in principle to resolve very narrow features in the optical domain. So this is a picture of something with 100 millihertz line width. So that's a Q of, on order greater than 10 to the 15. and that's really where the statistical precision comes from. In order to get that, of course, not only do you need an atomic system that affords that coherence with limited spontaneous decay, you also need an optical source that can support that level of coherence. And so there's another large fraction of what the experimental effort is in trying to make extremely well-defined sine waves in the optical domain. And so this is largely accomplished with stabilizing lasers to optical cavity systems. And so in the last few years, a significant amount of work has gone into building things like these cryogenically cooled optical cavities. For the most part, this technique is limited by thermal fluctuations in the optical cavities. And so simply cooling the cavities down does a lot for reducing this fundamental floor. Another interesting technology that our organizer, Marcus, has played a very big role in is the development of new types of really high reflectivity mirrors based upon crystalline materials that are just naturally less sensitive to these thermomechanical fluctuations. Here's a picture of a cryogenic sapphire system that we're working on in my lab. Okay, so the second pillar for these clocks working so well is quantum control. And maybe first and foremost, that comes from this magic wavelength optical lattice, the fact that the atoms can be trapped and essentially motion-free, nearly. Nominally, they're trapped in the so-called Lamb-Dickey regime, where you can view the atoms as almost being stationary objects. Doppler and motional effects are effectively made zero in this regime. But of course, you can't just do that in general, because the atoms are trapped in this optical field through the AC Stark shift. And so it'd be a pretty bad design, actually, to induce this really large AC Stark shift on an atomic sample that you're trying to interrogate so carefully. And so the key idea that makes this strategy possible for making a good clock is this magic wavelength, where here is the Stark shift, or AC polarizability, as a function of wavelength, and it's some particular laser wavelength the two match. And so you have, to lowest order, no Stark shift on the atomic transition. And so you can have the best of both worlds, tight confinement, without inducing strong perturbations on the atoms. So really the lattice does a lot of good things for you. It enables coherent probing of very large samples, and that's important for trying to keep the standard quantum limit low. I already mentioned that it allows you to trap the atoms, virtually eliminating all motional effects associated with the non-zero temperatures. It holds on to the atoms for a long time so that you can probe them for long interrogations, not milliseconds or microseconds, but for many seconds. And then I also mentioned that it does so in a first-order perturbation-free way. Okay, in order to load the atoms into the lattice, laser cooling plays an important role. And that's nothing new. Optical clocks have really been the pioneers in working on laser cooling on some of these narrowband transitions, these intercombination transitions, for example, and a lot of the group 2 atoms from 1s0 to triplet P1 were first demonstrated in optical clock systems and now are becoming more and more commonplace. In more recent years, we've even gone on to actually cooling on the clock transition itself. And of course, you can't really cool very efficiently on that transition simply because the scattering rate is so low. And so one needs to quench the excited population there. But doing so, we're able to efficiently use this as a way to typically drive population to the ground state of the optical lattice. And so this is a picture of motional sideband spectra, where we can see excitation not just of the atom electronically, but exciting some of the motional states. And after doing an extra stage of laser cooling on the clock transition, we're just able to bring them down to the ground motional state. So that's useful mostly for suppressing tunneling between the adjacent lattice sites. That actually does allow for a mechanism for Doppler shifts to sneak back into the problem. And so by eliminating tunneling, we can make that go away. And then it actually also plays another important role for suppressing atomic interactions. The most typical atomic species that are used in these clocks are fermionic. So we have ultra-cold fermions, and by simply cooling them down cold enough, we can suppress all of these odd wave interactions that identical fermions are allowed to interact on, and rely upon the Fermi statistics to prevent the even wave interactions. So this actually helps us quite a bit, removing cold collision effects between the lattice-trapped atoms. Okay, and then finally the third pillar was precision measurement. And so this is mostly just really characterizing very carefully exactly what the atom is experiencing and what perturbations might impact the operation of the clock system. So what I'm showing here is the polarizability for the two clock states in blue for the ground state, and the dashed line is for the excited clock state. And then on this side, this red curve corresponding to this left axis is just dimensionless plot of the black body spectrum. And importantly, you can see that there's actually some overlap in what the black body spectrum is with some of the polarizability down here at low frequencies. It turns out the single largest perturbation that we have to worry about is the stark shift due to black body radiation. And so this is one example of where we have to think hard about precision measurement. So in this case, we solve this by actually doing all of the laser cooling and the trapping of the atoms and the precision spectroscopy of the atoms inside kind of a controlled environment. This is our black body shield. It's just a copper structure that's lined with carbon nanotubes. The carbon nanotubes provide just a very highly emissive black body so that we basically can just know very well if we simply measure the temperature of the structure. We can calculate very simply what the radiative environment is experienced by the lattice-trapped atoms that are sitting in the middle of this. We naturally need some holes on the end to let atoms come in and go out, but because it's a nearly perfect black body in the inside, it's very simple to calculate what the impact of that is. Okay, so that's one example of precision measurement then. So kind of putting that all together, resting on those three pillars, a really good lattice clock today can get to kind of performance in terms of systematic uncertainty with what I'm showing here. Something like a part in 10 to the 18 is possible. Perhaps the single largest effect that we worry about the most is from black body stark that I just mentioned briefly. And the confinement in our optical lattice is actually really important too, because to lowest order, we don't have to worry about stark shifts, but there's higher order effects that do end up playing an important role. I don't want to say too much about that. There's a story to be told for every systematic shift here that we explore. But some of those stories are more interesting than others. But the take-home message here is that putting it all together, you can get to part in 10 to the 18, which on relative scale is about half a second out of the age of the universe. I think that's good to about one significant digit. I just read in the news that there's now some more disagreement about what the age of the universe is within some error bars. So at least to 1 sig fig, that's how well these clocks are doing. Okay, in terms of the statistical performance of these clocks, that's typically characterized by the stability, how much the ticking frequency of the clock varies over time. And we do conventionally characterize that with the Allen deviation, which is just a really nice way to visualize, really for any measurement, what the statistics, how the statistics evolve over time. And so this is showing basically the statistical precision as a function of averaging time. In this particular case, it's a pretty boring plot. It just averages down like white noise would, and so just with this constant slope. But importantly, you can see that at about 1 second, you can measure at about part in 10 to the 16. At longish times, so here for our very longest case where we ran for the better part of a day, in fact, more than a day, we're able to see stability down in the 19s, 3 or 4 10 to the minus 19. It's actually possible to improve upon that stability. There's been some nice work recently from Gilla showing that using one of their cryogenic cavities, you can get better short-term stability. Another approach for improving short-term stability is actually trying to make a hybrid clock by taking two atomic systems and referencing a single cavity stabilized laser to those. This is a so-called zero dead time clock. There's been work done in this area in microwave clocks and in atom interferometry, and we demonstrated for an optical clock that kind of making this type of zero dead time configuration where you're continuously probing the atoms, you can get stabilities down in the mid 10 to the minus 17 region at 1 second. So this is another way to kind of boost and improve performance using classical techniques.
What happens at
Yeah, so nothing particularly interesting. This is essentially the servo time constant associated with slaving the cavity stabilized laser to the atomic sample. And so actually it's almost misleading for me to plot this data up. It basically just represents really less than unity gain, and so the laser is not properly tracking the atomic transition at the shortest times. Okay, and finally, the last metric I'll mention for trying to understand how good is this clock is reproducibility. The idea, if we were to build two of these and make a measurement between them, do we actually get the same answer? In principle, you might expect that they would agree with each other within the systematic and statistical uncertainty that I just showed, but it's quite a challenging task to come up with a rigorous systematic evaluation. So it can be non-trivial to really realize the systematic uncertainty at the level that one estimates. And so it's always nice to be able to make direct comparisons between these two clock systems. So that's exactly what we did. We implemented a blinding protocol, perhaps like some of the electron EDM measurements that we heard about this morning, to try to prevent us from seeing the answer. But in the end, after making some measurements between two ytterbium systems over the course of a month, we were in fact able to see that they were consistent with each other at better than part in 10 to the 18 level. And so that's within the stated systematic uncertainty of 1.4 10 to the minus 18. Okay, so what does that mean? What does that buy us in terms of interesting capability? So I like to think about this reproducibility from a perspective of the gravitational redshift. In general, the two clocks that we compare against each other could be operated in different gravitational potentials, and we'd have to account for the redshift in making the measurement between those systems. And to do so along the surface of the Earth, it's conventional to relate the position of the clock to the geoid, which is this equipotential gravitational surface near sea level. And using the best techniques that we have at our disposal now, that was done recently in the last couple of years at NIST to try to relate what the geopotential at NIST is relative to the geoid. And in terms of clock uncertainty, the best ability to do that came in at about 6 times 10 to the minus 18, or something like a 6 centimeter uncertainty in what the geopotential was in Boulder there at NIST relative to the geoid. In some locations, it's possible to do better if you have a large density of gravitational measurements, if the location is particularly geodetically simple. Boulder, we happen to have the plains of Colorado right next to the mountains. So a number of factors can go into how well you can do, but state of the art is something like maybe about 3 centimeters or so. So the point is that this number is already larger than what the uncertainty now on the clocks is, and in fact, for the first time, the reproducibility of an actual measurement between these two clock systems. So in principle, you could say, well, there's no point in making these clocks any better because we're always going to be limited by gravitational effects on time. Of course, the clocks themselves may present the solution. An idea that's been around for a while now is to use the clocks to simply sample the local gravitational potential and basically use them as geodetic tools, the so-called relativistic geodesy. In order to really be serious about that, you would need to basically have a clock that's capable of measuring at a part in 10 to the 18, which is at the level where it outperforms existing geodesy, and then maybe you could improve upon those geodetic models. And so that's what we've shown now for the first time, is that you actually do have two clocks that when you compare them locally agree at that level. The next step would be to start moving one clock relative to the other over a very long baseline in order to actually make measurements that could improve geodesy. And that's something we're working on now, and along with several other groups trying to build up portable lattice clock systems.
Presumably, the air column also, or weather or pressure, let's say, also affects this? Is that much lower level than this?
Yeah, so there definitely are, in general, tidal effects from changes in ocean, land, and atmospheric, and these things are generally studied and reasonably well known. However, for the most part, it's based upon models and experiments that can help measure some of those effects. I think would complement nicely existing experimental evidence. So I think that one of the reasons geodesists are excited about this is the potential to explore dynamical variations in the gravitational potential. Okay, of course, in order to do that, that requires having really good clock stability at short time scales, but that's exactly what optical lattice clocks are good at doing. Okay, so taking that type of a device then, how can we use this to explore a variety of different fundamental physics tests? So I've shown up here, there's our clock transition between our ground and excited state, and we've measured the transition frequency using the best measurements we can relative to cesium, this optical frequency out to an uncertainty of about 100 millihertz. The question is, well, why is it that that is the transition frequency for ytterbium? That's what Mother Nature has given to us. So if we take a look at a simple expression, this is the Dirac model of the hydrogen energies. And we can see that that energy scales with a number of quantum numbers as well as the fine structure constant alpha. And what if alpha was varying? Then presumably our bound electron energies would be changing. And so you could parameterize that, scaling that if alpha did vary, there would be some sensitivity K that would impact the measurements of these eigenenergies. And of course, as most here know more than me, that there's actually a number of theories that ultimately predict or even insist on this type of variation occurring. And so we want to use the clock systems to explore this a little bit. So I'll describe, I hope in brief, 3 different measurements that we've made over the last year or two that kind of explore how we can use these next generation clock systems to try to probe some of these new physics. So the first one is I'll describe measurements of the absolute frequency of ytterbium made with cesium clocks, cesium fountain clocks that are scattered around the world. And in a lot of similarity to the measurements I mentioned at the beginning by way of introduction, this was exploring a local position invariance. And we extended that to looking for gravitational coupling of the fundamental constants. Second, I'll describe some frequency ratio measurements that we've been carrying out between optical clocks located in Boulder. And this really has the potential to unleash the power of the optical clocks because it's measurements between different types of optical clocks. They're not limited by the more conventional clock systems. And then finally, I'll briefly describe some efforts for making a global observatory of optical clocks for looking at dark matter coupling. Okay, so first the absolute frequency measurements. So right now, the hertz and the second are defined in terms of cesium. And so if we want to measure the transition frequency for ytterbium, that has to be relative to cesium. And so we carried out a series of measurements to do that. Because the cesium clocks typically have much worse statistical performance, really good absolute frequency measurements take a long time. Often they take many weeks or months, sometimes even longer. In this case, things were a little bit complicated in that the cesium fountain clock that normally operates at NIST, it actually hasn't been operating for a couple of years. They've been making some rework on that system. And so we carried out these measurements via a satellite time transfer to a number of fountain clocks, mostly located in Europe. So we have our ytterbium system that was linked by an optical frequency comb to a hydrogen maser. And that hydrogen maser is sitting right there. And we basically count the difference between the hydrogen maser and our down-converted ytterbium signal. The hydrogen maser itself was linked to an ensemble of hydrogen masers maintained at NIST as part of the NIST timescale. And then that is basically broadcast over satellite time transfer physically it goes to Braunschweig, Germany, where as part of the responsibilities of the BIPM, they maintain a collection of international standards and develop the International Atomic Time. And so it's through that mechanism that we're able to make these measurements of ytterbium to the cesium system. So we did so over about a 6 or 7 month period. The data is shown here. This is just showing a frequency correction to the maser over time. And when we simply scale that relative to what the accepted frequency is for the ytterbium transition, the internationally accepted frequency, that's now this axis over that same time, and I've simply binned the data into month-long intervals. To look for possible variations in local position invariance, borrowing the similar strategy from what's been done in other experiments, we simply look for variations that might coincide with the Earth orbital period. And in this case, because of it was about 7.5 months, we were able to see just a little bit more than half of that period. And generally speaking, we benefit from the fact that these are actually basically state-of-the-art measurements right now. The error bars on these are exceptionally low. They're actually the lowest that's ever been done for an optical transition. So putting that all together, we're able to get a constraint on the LPI violation at something like a 10 to the minus 6. Now, if you were paying really close attention, that earlier experiment I mentioned involving hydrogen and rubidium, that was actually in the 7s. So this doesn't compare to that measurement. Part of the reason is because it's an 8-month measurement and not a 14-year measurement. And you can't get around the fact that you need a long time for this, in part because both these measurements are involving cesium clocks that take a long time to average down for the most part. And so you would need to continue this for a much longer period of time to really outperform that existing measurement. But there is something interesting that you can do. So were an LP violation to actually be there, you could motivate it coming from one of 3 different possible mechanisms. It could come from a variation in the fine structure constant. It could also come from variations of other fundamental constants like the electron to proton mass ratio or even in the quark mass. Each one of those has a potential to impact the ticking rate of these clock systems. And of course, each one of those would vary depending upon the change in the gravitational potential as the Earth orbits the Sun, delta phi. Okay, so simply what we did then is we said, well, listen, we've made a bunch of measurements of ytterbium versus cesium. There's been other optical clocks and atomic clock systems that have made measurements themselves, and each one of them has different degrees of sensitivity to these possible variations of these fundamental constants. So, for example, there was some measurements made a few years ago between aluminum and mercury. These are both optical clocks, and it's known that optical clocks essentially only have sensitivity to alpha variation. And so there's variation to alpha, but no sensitivity to the light quark mass or the electron to proton mass ratio. On the other hand, there's measurements between hydrogen and cesium that actually maintain sensitivity to 2 of those possible fundamental constant variation. And finally, ours maintained mostly sensitivity to the first and the third and not the second. And the basic idea is basically these are as almost orthogonal as you could hope for in most cases. And so by combining analysis of all 3 of these measurements, we're able to get to a final determination of how much possible gravitational variation is there for the electron to proton mass ratio. And here, benefiting from our new results as well as some of the other works that were done, we're able to put roughly about a factor of 5 improvement on previous constraints. All right, so this is just one example of how we could use these types of clock systems for analyzing existing data to look for new physics. Okay, so something a little bit more interesting, I think, here is now describing measurements that we've been carrying out over the last year or two, looking at optical clock comparisons between different clock systems in Boulder. So we have at NIST the aluminum quantum logic clock, the ytterbium clock that we've been talking mostly about so far, and the strontium lattice clock as well. And they're all connected to each other, nominally over fiber link. There's really only about a few tens of meters between the labs where these clock systems are, and there's really only about 1 kilometer between those, and so we have fiber links linking them back and forth. And basically we carried out about a year-long campaign making measurements between these systems. So I think inspired by some of the kind of really cool collaboration names that many of you have, Acme, Magis, we tried to come up with one as well. It's the Boulder Atomic Clock Optical Network. And who doesn't like bacon, huh? Okay, so one really cool thing, kind of that one thing that I think makes the cool factor on this measurement a little bit higher than normal is that in the link between some of the different clocks, there's not just a fiber-mediated link, but we're actually shooting laser beams in the air between the main NIST site here at the base of the mountain and between the Gila Tower to connect the strontium and ytterbium clocks. So there's a femtosecond pulse laser system that we're shining back and forth. We've got a permit from the city of Boulder to do that. And that actually allows us to transfer frequency exceptionally well. This is work done led by Nate Newberry and colleagues. So you can kind of see the statistical performance of this type of a measurement. So what you're seeing here in red and green is the stability of measurements between aluminum ytterbium and aluminum strontium measurements. And then in blue is between the strontium ytterbium measurements. And then finally, all of the noise contributions from like that free space transfer I just mentioned, from the fiber transfer, which is that fiber network is called the brand network, and then finally by the comb systems that allow us to jump from one optical frequency to another. And importantly, you'll see that the stability here is nominally set by that of the aluminum clock. They've only got a single quantum absorber, and so their quantum projection noise is much higher. For the ytterbium strontium clocks, both of those systems have a large atom number, and so generally the stability is better. We're operating close to the quantum projection noise, but not quite. And then all of these technical noise sources are well below the clocks themselves. Okay, so the results of these measurements that have really gone on for the better part of a year are kind of shown here, where what we're looking at is what is basically the frequency ratio between the different clock systems as measured from November all the way to June. And this is for aluminum ytterbium, aluminum strontium, and ytterbium strontium. And for someone like me, this is already really exciting because this gives us a chance to look at the ratio of these clock systems and then compare it with ratios that are made by other laboratories around the world. This gives us basically a tool, a means to try to characterize whether or not these clocks are really as good as what we think they are. And this is important on the path to redefining the SI second. But probably to most people, what's on here is not terribly interesting. What we can take this same data, though, and analyze it in a different context, looking for possible dark matter signatures. So we've already heard some discussion on this from this morning, that most dark matter models allow for some non-gravitational interaction portal, and it might look something like this. This is assuming a scalar potential and a linear interaction term between dark matter and between normal matter. In this particular case, we're looking at coupling between the dark matter potential and the electromagnetic field tensor. And it can be shown that if such an interaction occurs, that it would lead to a modulation of the fine structure constant. And so, therefore, we can try to use our clock data to look for some types of dark matter, like this ultralight scalar dark matter that, as was mentioned this morning, one of its signatures would be that essentially it nominally operates like a classical field, oscillating at the Compton frequency. And so we can simply try to look for oscillations in measurements between the different optical clock systems. And in particular, we can try to look for correlations between all the measurements to try to constrain whether or not we can resolve any of these sinusoidal variations. And this basically summarizes that effort right here. So this is basically looking at the strength of possible interactions with dark matter. This is parameterized with this dimensionless parameter d. that basically scales with 1 over the energy scale for the dark matter interaction. And then this is shown as a function of effectively the mass of the dark matter, of the unknown ultralight dark matter particle. And importantly, we're showing just a handful of different results from the past few years, nominally taken with different forms of spectroscopy like dysprosium or rubidium cesium spectroscopy. So I guess importantly, because the optical clocks offer really good performance, they're able to improve in general upon some of the constraints. So the purple and the green data here are some of these optical clock measurements. It should be or could be better than what we're seeing here, but most of the optical clock species that we're using don't actually have a lot of sensitivity to fundamental constant variation like alpha. Ytterbium is basically the biggest one. But important, and this green data that you're seeing is actually measurements between the aluminum ion and mercury ion clock system that were from several years ago. And mercury ion just has very high sensitivity to possible variation of alpha. So in the end, that gave the best constraint at these really low masses. Okay, importantly though, this is kind of a stepping stone for us. This was the first round of measurements that we're making, and right now we're actually in the lab working on doing some correlation measurements that would allow us to basically make measurements that are with an improved quantum projection noise limit for this single trapped ion, the aluminum quantum logic clock. So we're hoping to get as much as an order of magnitude improvement on this here in the near future. Okay, I think I've only got a couple minutes left. Okay, so I'll finish just by briefly talking about a search for maybe a related but different type of dark matter, the so-called topological dark matter, perhaps still an ultralight candidate, but normal matter is clumpy, and so perhaps we would expect dark matter to be the same. As our galaxy rotates around, we would expect that there would be this dark matter wind moving at about 300 kilometers per second, and perhaps we can observe some transient effect associated with that clumpy dark matter moving through our clock systems. Okay, so for this particular measurement, we took advantage of a peculiarity of the optical clock systems in that really these optical clocks are constructed of two basic building blocks that both have precision measurement capabilities. One is the atomic system with really high coherence, and the other one is the laser system with really high coherence. And in principle, were something like alpha variation to occur, it would impact those two subsystems in different ways. So nominally for the atomic system, it would scale as alpha squared plus some relativistic corrections. And for the cavity systems, it would actually vary linearly in alpha. And so the fact that these have different scaling means that just making one optical clock gives us a tool for exploring some of these signatures, perhaps some transient topological effects. So in principle, you could make an interesting dark matter search out of just a single clock. In practice, you'd be a lot better off using two clocks and looking for correlations between those. But you wouldn't necessarily need a formal link between those two clock systems. You could have two clocks operate in different locations and simply kind of timestamp making measurements of the relative cavity to atom system frequency changes, and then simply cross-correlate them later. That's basically what we've done. There's part of a global observatory involving labs at NIST and the Paris Observatory, Poland, and Tokyo. We looked at data where we happened to be running the clock systems at the same time and cross-correlated them. So here's some of the frequency data, and here's some of the cross-correlation between them, looking for possible signatures of transient signals from topological dark matter. And through that analysis, we're able to put some constraints on the possible coupling strength between dark matter. And so the constraints, I'll just, for time, we'll just look at this plot here. This is basically showing that coupling parameter lambda, the energy scale, as a function of the possible defect size for the topological defect. And there's been work on this before looking at the GPS clocks, and then more recently looking at different strontium lattice clocks, and then this international collaboration benefiting from some improved performance was able to see 1 to 1.5 orders of magnitude improvement. So again, no interesting signatures, just constraining and observing, putting important constraints on the possible interactions. Okay, so to finish, I'll just kind of look back to look ahead. The very best microwave atomic clocks that we have today are the cesium fountains. And these things typically achieve a line quality factor of 10 to the 10. And they're able to split that line down at 1 part per million. And putting that together, they get 1 part in 10 to the 16 performance. For our optical clocks, we're able to achieve a line quality factor of 10 to the 16. And even a conservative estimate, if you say that maybe we can only split the line for technical reasons down to maybe 100 part per million, it seems promising that in the future we'll get to the 10 to minus 20 domain. And so hopefully there's a couple more orders of magnitude that we can really make significant improvements on some of these new physics searches. So with that, I'll go ahead and end. I'll just want to definitely acknowledge the folks that played such a big role in this work. In particular, Will McGrew and Xiaogang Zhang were a student and a postdoc who contributed significantly to a lot of the things that I showed. And then I highlighted a number of collaborations. So the ytterbium cesium measurements were a collaboration between 3 different groups at NIST, the Atomic Standards Group and the Network Synchronization Group. The optical ratio measurements was a large collaboration, that Bacon collaboration involving the ytterbium aluminum clocks and the strontium clock at Gila, and a number of groups working on the transfer and the optical frequency combs. And then finally, that international observatory was linking groups from NIST, NICT in Japan, LNI CERT in Paris, and the Institute of Physics in Poland. Yeah, and I'll go ahead and stop there. Thanks for your attention.
So would you say for time variation of fundamental constants, there's a push to improve cesium or rubidium?
I mean, I would say in general right now, I think there's an overall feeling from their community that they're kind of hitting the limits in terms of what they can achieve in terms of long-term stability and accuracy, that there's only very marginal gains to be had. There has been some efforts to try to improve the short-term performance with using the best local oscillators they can, and that can translate to, on some time scales, better limits from those types of systems. But for the most part, what I see is that there has been in the last 5 years a shift in energy into the optical domain. And I mean, there's already been a strong effort in the research community in the optical world. That's been going on for decades, but in the kind of more stricter metrology community, I'd say that there's been a little bit shift in energy, that the inevitable is happening, that the optical clocks are maturing enough that they're saying, well, if we have finite resources, maybe it's best to invest in this right now. That's at least what I see.
I was just thinking from the science output perspective that, you know, if you really require have the cesium and rubidium as part of the, you know, the clock comparisons, saying is there a scientific argument? If there was a scientific argument for another factor of 10, then I would say maybe people would get creative and, you know, look for ways of doing that. But, you know, if the scientific argument's not there, then
Yeah, and perhaps part of the scientific argument now is the pragmatic issue, that's where some of the existing definitions and the existing standards, you know, exist, and in principle that's an evolving picture now, and so that changes a little bit the nuances of that. So anyways, there definitely are some efforts. There, you know, cryogenic fountains. There's been some efforts over the last few years, and that's something that people continue to work on. But I would say it's probably not as intense as some of the work in other areas.
When you show your data, especially with long averaging and then over a period of 6 months or a year or something. Is it possible, from the way data is taken, to actually stack it and look at, for instance, daily variations and so on? Or have you looked at it?
So you're saying, for example, let's say we ran on Tuesday and Thursday, but both from 9 a.m. to noon or something, to overlap that, data, average it, and try to look for some diurnal variation.
Yeah.
Yeah, no, in principle you could. In practice, we do that a little bit, mostly as we're trying to be careful to randomly sample over the diurnal variation to make sure that we're not always taking data at the same time. But we haven't ever intentionally tried to take data at the same time for that purpose.
Or
Now,
interpret the old data the same way, right? I mean, you can take the data that exists, just again, I would say, wrap it around with a 24-hour cycle, so let's see if there is any effect, which could be just instrumental at that point.
Yeah. So generally, we haven't done that. That is something that will probably change, mostly as we have the ability to do high accuracy measurements over long baselines. So, due to these tidal effects, it's known that the gravitational redshift should vary at the kind of 10 to the minus 17 level. And so now that we're measuring at 10 to the minus 18, we could see that. The only reason we don't now is because every good clock measurement that's been made at near that level is with two clocks that are really close together, so they're experiencing the same potential. But at the moment we're able to make long baseline measurements, that we'll see that instantly, and that'll be something interesting to look at. Yeah.
Could you show again, it's about 6 slides back, that time series, that long duration?
Let's see.
Right before, yeah, okay.
This one?
So that shows just a short time scale right there, right?
That's right. So this was one day of measurement.
But your next slide has many, many days, obviously.
Yeah, that's right. Yeah, so this is a combination of, so if I go back to this, so we measured over, in this particular case, some like 20 days scattered over something like a 7-month period. Yeah, and so in the end, this is the type of data. Basically, each one of those data points has a data set like this, and then by appropriately accounting for the dead time between the measurements, we can still essentially fit that to a sine wave and try to constrain, if that's what your question was here, try to offer some constraint.
I'm just wondering why you have a month of data roughly in that longer thing. How do you get down to 10 to the minus 22, which is like 10 to the minus 8 seconds?
Yeah, so technically the data that I was showing you there goes with this purple curve. So we get down to 10 to the minus 21. The 10 to the minus 22 here with the mercury measurements, so those actually went over something like a year and a half. And so that's the time scale there.
And the one that goes down to 10 to the minus 23?
Yeah, so these were rubidium cesium measurements that was tracking the better part of a decade.
Last question.
Remember when you look for daily variations, look for sidereal, don't look for diurnal variations, because even your wonderful clocks, you will see diurnal variations, but when you've got months and months of data, go look for the inertial don't look relative to the sun.
Yeah.
And also in some of the annual variations you're looking for, you ought to be sensitive to velocity changes as well. And while once again what you were saying that the clock transitions are often really insensitive to a bunch of things you'd like to measure, you're still when you're looking at different times in the year, you've got different velocities, and so you should have the time component of whatever angle dependence might, as well as position dependence.
So won't that affect all clocks the same, velocity?
For most of the measurements we've done, yes, but again, maybe once we start going to these long baselines, maybe some new possibilities open up.
But the effect is basically species independent. It's a Doppler shift.
Not, no, but there's also, in Kosolevsky's standard model extension, there are definitely species-dependent ones, and you should be able to say interesting when it's on.
Yeah.
All right. Okay. With that, once we get into Kosolevsky's infinity of parameters, let's thank Andrew